Alrighty, well, this will be our final exam review for the course. Good news is, of course, that you've already seen what the exams are like, and the final exam will be very similar, same format. I created the original tests, and I create the final exam. It's not a departmental exam or anything like that. So you already know what the test is going to look like. You know what types of questions are going to be asked. So there's not going to be any surprises there. What to expect in terms of topics? Well, this is cumulative. So basically, if you want to know what to study, all the topics we've covered. Now, I always hated to hear that as a student because that's not very helpful. But what I mean by that is, if you look at the tests you were given over the course of the semester, I gave specific questions on specific topics. And so that means I felt those topics were important enough to ask questions on. Well, obviously, with the final exam, I'm going to think the same way. And so the best thing to understand is, if you got questions on the midterm type exams, then you're likely to get similar type questions, or at least questions on the same topics on the final. How long will the exam be? Well, you can expect it about twice as long as a regular test. I'm going to model this exam as if it's a 2-hour exam, and the normal exams we've taken have been 1-hour type exams. And so if a regular exam has about 6 or 7 questions, let's say, then you can expect the final exam will have between 12 and 14, twice as many, basically. The good news about that, of course, is if you miss a question, or if you have trouble with a question, each question is worth less. If I give you a test that only has 3 questions on it, then each question is worth 33 points. So if you do bad on just one question, you're already down to a 63. Whereas if you have, more numerous questions, then each question is not worth all that much. So if you make a mistake on a question, it's not as harmful. Now, let us go ahead and be a little more specific on the topics. Remembering back over the course of the semester, the first real topic we discussed in physics was kinematics. And with kinematics, this was basically the types of questions like a bird is flying with a certain velocity for a certain period of time, then wind hits the bird, gives it an acceleration for a second period of time. How far does the bird go? How fast is it moving? Or you shoot a cannonball at an angle of 30 degrees with a certain velocity. What's the maximum height reached by the ball? Or what's the time of flight? So all those types of questions that had to do with distance and velocity and acceleration on the kinematics equation style, that's what I'm talking about here. Big things to note, of course, X and Y components. So for instance, if you have a question of a ball being thrown from the top of a cliff, and you want to know how long will it take for the ball to hit the ground, well, you have to worry about the fact that the ball moves both horizontally and vertically. So vertically, gravity exists, and so there's some acceleration due to gravity, but horizontally, there is no acceleration, because once you've thrown the ball, it just keeps moving horizontally without speeding up or slowing down. And so you have to separate all the horizontal stuff, all the X component stuff, from all the Y component stuff. And just be sure that they're independent from each other, and work the kinematics equations on X and Y separately. Of course, along with X and Y components, you have to know, if like the cannonball, let's say is shot from a cliff at an angle of 30 degrees. Well, you have to know how do you get the x and y components of the initial velocity. Because when you go to use the kinematics equations and you have to plug in initial velocity, well, you can't just plug the regular velocity in because that's at an angle. Instead, you have to work either in the x direction or the y direction. So the first step is going to be, given a velocity that's at an angle, can you break that velocity up into x and y components first? And then you use the x and y components to solve for whatever it is you need to solve for. So all that kind of stuff, that's usually where a lot of the mistakes come in, the problems come in, is we know what equations are there. We have the formula sheet in front of us to use the equations. But do we use x component stuff or do we use y? If I want to use the y component, is that a sine or is that cosine? That stuff you just have to practice, and if you practice enough, you become very familiar with it. Once we were done with kinematics, we moved on to Newton's laws. And Newton's laws had F equals ma. And frictional force. So you apply forces to an object. What's going to be its acceleration? An object slides down a ramp, or you push on a block on a horizontal table. The table has some friction. What's the acceleration? You have to calculate the normal force. Along with Newton's laws, we also had things like the third law, which was the style of question, you have multiple blocks connected by ropes, and you pull on the system with a certain force, and you want to know the tension in each rope. Also, you had elevator problems. So a person is in an elevator, they're standing on a weight scale, and you want to know, depending on how the elevator moves, do they feel heavier? Do they feel lighter? What would the weight scale say? Things like that. And we also had pulley questions. So, we could have a pulley like this, where there's a block here connected to a pulley, and there's a block over here. This has a mass, this has some other mass. And you want to know what's the tension in the rope, and what's the acceleration of the blocks. And the trick for this, of course, you're still using F equals ma. It's just that since now there's two blocks, you have to use F equals ma on each block separately. So this block, this will have m1g downwards, and this will have tension upwards. This block will just have tension to the right. The mg for him doesn't count because that's vertical, but notice that this block moves horizontally. So when you do F equals ma for the block up on the table, you only need to worry about the x forces. So you won't use mg for that one. But for the yellow one, that block is moving vertically, so you need all the y forces. But anyway, you use F equals ma for both. You wind up with two equations with two unknowns. Both equations have tension in it, and both equations have acceleration. And you just use whatever method you want, algebraically, to solve for tension and acceleration. So those were the types of questions that went along with Newton's laws. Once we were done with Newton's laws, we had work. And so remember work, this was you apply some set of forces to an object. The object moves a certain distance, and you want to know how much work is done, and you want to know how fast will the object be moving. And so for this, work is force times distance, where that's a special dot product. And you just had to remember, if you want to calculate the work, then first ask yourself, what direction will this object move, x or y? Once you know the direction the object's going to move, let's say x, just as an example. Then, for the forces, you only need the x forces. Because what the dot product says is you multiply the force times the distance, but only the components which are in the same direction. So if my block moves in the y direction, I only need the y forces. And if the force is in the same direction, it's positive. If it's in the opposite direction, it's negative for work. Okay? And again, the work energy theorem says work is change in kinetic energy. So if I know how much work is done, or I just calculated it, but I now want to know how fast the object will be moving, well then I just say that's 1/2 mv squared. So that's work and the work energy theorem. From there we went to conservation of energy. And with conservation of energy, of course, the big equation, kinetic initial plus potential initial, is kinetic final plus potential final, where we know kinetic energy is 1/2 mv squared. Potential energy, there's two of them you have to worry about. One is mgh, that's for gravitational potential energy, so an object that's at some height. And the other is spring, 1/2 kx squared. If you're compressing or stretching a spring, there's some potential energy there as well. And so we would have some system, and you'd write out your equation, and then you'd ask yourself questions. You'd say, okay, at the initial state, is my object moving? If it is, then I have 1/2 mv squared. If it's not moving, then it's 0. Then you'd ask, is the object at some height? If it is, mgh. If not, 0. And then, am I already messing with a spring? If so, 1/2 kx squared. If not, 0. And once you ask those questions, that would let you write down all the initial stuff. And then you look at the final side, and you say, for the final side, same questions. And I'll tell you what to put on the right side of the equation. Once you have it all written out, there's only going to be one unknown sitting there, depending on what the question's asking. And you just move things around algebraically to solve for your unknown. So the key is to be able to ask those questions to yourself and be able to answer them. If you can answer those questions, then you can fill out this equation fairly easily. After energy, we started into rotation. And we had rotational kinematics. Which is basically a repeat of the original kinematics, except instead of x, you have theta, which is angular displacement, or how far around does the object go, how many times does it spin, through what angle does it spin. All those things are like the distance equivalent for rotational kinematics. Instead of v, you have omega, so velocity becomes angular velocity, and acceleration becomes angular acceleration alpha. And once you know those, then all your old kinematics equations, you just replace those variables with these rotational ones, and you have your new equations. And you go through the questions just like you did before. Which equation should I use? Well, I'm looking for alpha, and I have VF, and I have V naught, and I have theta. So I probably want to use VF squared as V naught squared plus 2 alpha theta. That'll give me my alpha. Another thing to remember is units, radians, not revolutions. Okay? So if you're given some data in your question that talks about RPM, or revolutions per minute, or revolutions per second, or something like that, then you have to convert into radians first. And a conversion was 1 revolution is 2 pi radians. So if you know that, then you say, okay, the thing moved or spun 3 revolutions. Well, that's 3 times 2 pi, which is 6 pi radians. So easy conversion. But you have to do the conversion. You have to have the correct units for everything. All right, once we were done with rotational kinematics, we then went to torque. And torque was a pretty interesting topic. Here we had some of the torques is equal to 0, or torque is R cross F, depending on the type of question. R cross F, these were the ones where, you know, you have a wrench with a bolt and you apply a force, and you know the length of this wrench is some length. And the question is how much torque is applied when this force is applied to the wrench or whatever. And remember, R cross F was similar to like when we talked about work. We're talking about force times distance, but instead of the dot product, we're now using the cross product. And what the cross product means is perpendicular things. So if you look here at the wrench, let's say, is vertically set. The handle is vertical. So the distance means the distance from the point of rotation to where the force is being applied. That's a vertical distance. And so the only force that would give rise to a torque is that component of the force which is perpendicular to the distance. So if the distance is vertical, then you only care about horizontal forces. It's the exact opposite of work. With work, you want the force and the distance to be in the same direction. With torque, you want them to be perpendicular to each other. Now the other one, the sum of the torques is equal to 0, those were the balancing type questions. You know, you have a seesaw or a meter stick or something supported by a fulcrum, and then you have weights hanging at some distance, and you want to say what kind of weight should I put over here such that this thing is in equilibrium. Or you have a brick wall and a tent or a signpost holding up a sign, and there's some, you know, wire holding up the pole. And the question is, what should be the tension in this wire such that the pole is in equilibrium? Well, again, that's balancing things. If you add up all the torques, it should be equal to 0. What are all the torques? Well, you have a torque due to this force, you have a torque due to the weight of the pole, and you have a torque due to the tension in the wire. So you'd say torque 1 plus torque 2 plus torque 3 is equal to 0. And then you plug in whatever the torques are, R cross F for each of them. Some of them are positive, some of them are negative. How do you know when they're positive? The rule is, if the force makes the object rotate counterclockwise, we generally call that a positive torque. It's just a standard that was chosen arbitrarily. It's chosen for a certain reason, but doesn't matter what the reason is. That's what the standard is. It doesn't have to be that. You can make it the opposite. But if you make it the opposite, you have to put on your picture, my positive is clockwise. Because if I don't see that, then I'm going to assume you're doing everything backwards. So those were the torque style of questions. The last topic we had was rotational energy. And rotational energy was very similar to conservation of energy. In fact, it was identical, except every question we had before had things which were sliding down the hill or things like that. Whereas now things can roll because they're allowed to spin. And so what did we have to change? The equation was identical, except now kinetic energy had two pieces. 1/2 mv squared for its linear motion, and 1/2 I omega squared for its rotational. That's the only change. And what we found, the trick to solving these problems, was to use whatever I is, you replace it with, I don't know what this number is, you know, some number, times mr squared, where this number depends on the shape. Is it a sphere? Is it a ring? Is it a cylinder? Each one of those things has a different number out in front. Is it 2/5? Is it 1/2? Is it 1? But that's the moment of inertia. So when you write down your conservation of energy equation, when you see an I, you would plug this in instead of the I. And also, the other change you would make is you would say omega is V over R. So everywhere you see an omega, instead of writing omega, you'd write V over R. Once you made those two substitutions, then you'd have your standard conservation of energy equation written out, but everything is terms of M and V. There's no R's, there's no I's, there's no omegas. All the weird variables have canceled out, and you're left with just the standard ones that you could solve for. So if you know how to do regular conservation of energy, then you already know how to do rotational. The only difference is adding in this one little extra term and knowing how to use it. This also means likely, given on a test, first of all, you have to be very careful to read the problem, because if I say something slides down the hill, you don't have rotation. But if I say something rolls down a hill, then you do have rotation. That's how you know which to use. But these are all the topics. That's everything we've gone through this semester. Unfortunately, we had to leave a couple of things out just because of timing issues and things. Now, how should you study? Given that there's a limited amount of time, what I would do is I would take your tests, the tests you've already taken, redo the tests, make sure you know how to do them. If you have any problems with any of the questions, or you want to find out if you did it right or anything like that, you can email me and I'll be happy to look over it. But redo the tests first. Because if I already gave you questions like that, then I found those questions to be important. That doesn't mean I'm only going to give you those types of questions on the final exam, obviously. But it means if you can handle those exam questions, then likely any other type of question I give you, you should be able to handle as well. They'll be similar. Next, because these rotational things we didn't have a test on yet, I would be sure to practice those practice problems first, along with the tests. And make sure you know how to do these practice problems. Once that's finished, then I would go back and look at the practice problems for the older topics. Okay? And in fact, when you do your old tests, make a note of which topics you're having most trouble with. If you're killing it with conservation of energy, then fine. Don't worry about going back and doing more practice problems. You know how to do it. But if you're having trouble with kinematics, then make a note, and kinematics problems are the ones you should practice from the practice problems. Or, I was having trouble with the inclined plane stuff. Let me look back at inclined plane practice problems. Okay. So, do your tests over again. Blank sheet of paper. Start from the beginning as if it's a test. See if you could work through them. Then, practice the practice problems from rotation, because you will have questions on the final exam with those, since you haven't had them on your other tests. Once all that's done, if you still have time left over, that's when you go back to the old practice problems from the other topics, just to get more practice in. But certainly, you know the format of the tests, you've seen the kinds of questions I offer. You will have the formula sheet again with the test. Moment of inertia, I will give them on the test paper, so you don't have to memorize, the cylinder is 1/2 mv squared, or 1/2 mr squared, or anything like that. So nothing to memorize, just understanding how to work these problems. Be sure, when you are solving test problems, that you solve the problem on the test, and you don't solve a homework problem. I've seen multiple examples of The fact that I gave a question similar to a homework problem on a test, and when students were solving the test question, they would use the numbers that were used in the homework rather than the test. Well, all that tells me is you have no idea what you're doing. You're just copying homework. I don't mind you using your homework and your notes and stuff as a guide to remind you how to solve a problem. But if you're just going to take word for word or line by line what you did in the homework and copy it down on a test, I don't see why I should give you credit, because you're not solving the question that's on the test. So be very careful about that. It's easy when you're rushing and you get things confused, but there's no reason to rush, since this is not a timed exam. This is given online. You'll be able to download the test. So there's no need to rush. Make sure that the questions you're answering are the questions posed on the test, not from elsewhere, because I don't want to see homework numbers on the test questions. Anyway, that's all I have for the final exam review. Not much left to say, other than please feel free to email me if you have any questions. If you need to go over any topics, or you're working out a question and you want to make sure you're doing it correctly, I'll be happy to look over it. I'll just send a picture of the question or whatever, your work. And if I need to send my own picture of the solution to you, I'll be happy to do that. But other than that, I will see you for the final. The final exam will be given Thursday. I'll post it in the morning. And as I said in the email, because some students may have exams on Thursday, some may have it on Friday, you're free to submit the final solutions and everything Friday by 11:59 p.m. I recommend you don't wait till Friday to work on the test. You should do it Thursday if you can, because you never know if something comes up at home and you have to postpone finishing or whatever. And also, you want to be sure to try to submit the test early, so that if there's an issue with your computer where it doesn't submit properly, it's not accepting it, you can still contact me before the deadline is over. That's very important, because I, of course, have multiple classes just like you all do, and I have to be able to have everything graded for when the school wants all the grades submitted. And so I won't be able to take a late submitted final exam because I'll be too busy trying to finish up grading for all my classes. I need everything in on time. The only other thing is, be sure when you submit the final exam that you do not just submit the solutions. I need to see the work as well. If all I have are answers, just number answers, then I can't give you full credit. Especially if the answer is wrong, then I can't give you any partial credit whatsoever. That's a big mistake. But even if the question's right, how am I supposed to know how you got these answers? How do I know you didn't just talk to somebody in class? You have to show your work. Now, if you want to show the work on a separate sheet of paper or whatever you want to do, that's fine. If you don't want to work it out on the test paper. But I need to see the work with the solutions. All right, so I think that's it. Thursday morning, the exam will be posted on Canvas. Download it just like the other exams. Work it out. If there are any issues, email me as soon as you can so I can correct any mistakes I might have. It will be due Friday by 11:59 p.m. But try to submit it as early as possible just to avoid any technical issues cropping up. Other than that, I wish you all luck.